Welcome to statics. This is a problem where we are reducing this distributed load into a single resultant force that will act somewhere on the beam, and we've been told to use A as our reference point. So step one is find the resultant force, find FR. And so let's get started by making an observation about the loads. And so I see three shapes here, or at least I want to break it up into three shapes. I can see this first shape up here, which is a triangle, and I'm going to call that area 1. The second shape I see is a rectangle down here, and I'm going to call that area 2. And then the third shape I see is another rectangle, and I'm going to call that rectangle area number 3. And so I've broken these up and numbered them because it's going to help you follow along with what I'm doing. So the resultant force from area 1 will equal area 1 is a triangle, and so the area of a triangle is the half times the base times the height. And so in this case it will be a half times the base, and so I need to add dimensions to this problem. And so this problem begins at 0. Right here it is 0. Over here it is 4.5. We are in units of meters. And so what I mean is that the distance between here and here is 4.5 meters. And the distance between B and the end is another 1.5 meters. All right, so we have dimensions now. So half the base is 4.5 meters. And then what is the height? The height, if you look back in the problem statement, we see 6 kilonewtons per meter up here. I'm going to highlight that. But that's the total height, and so we notice that this triangle begins at a different height, and looks to me like it begins at 3 kilonewtons per meter, which is the value over here. So if that value over there is 3 kilonewtons per meter, so is this. Okay, so we have half times the base times the height, so this is the base, that's our half, and our height is 6 minus 3, which is 3 kilonewtons. And so our resultant for that area 1, the resultant force, will therefore equal 6.75 kilonewtons. Now, that is negative, or another way to think of it is that it's pointing downward, and so let's kind of keep track of that by doing that. So let's move on and now discuss area 2. So area 2 is a rectangle, and that's easy to calculate the area. We have F resultant area 2 is just equal to the base times the height, which is equal to 4.5 again, meters, and we multiply by 3 kilonewtons per meter, and so we end up with 13.5 kilonewtons. And this is again pointing in the downward direction, or it is negative. The third area we have is shown up here. I'm going to make it yellow so that we can kind of see what area I'm talking about now. So I'm talking about this area right here. This area is area 3. And so the resultant force for area 3 is, again, the base times the height. And so in this case we have 1.5, and I'm going to write the units in so we realize what's going on here, and then we multiply by 3 kilonewtons per meter, and therefore that is minus 4.5 kilonewtons. All right, so we have calculated all the resultant forces of these individuals, And so I am now going to sum them up. So the, the total resultant force, I'll write total, is just going to equal F1 plus F2 plus F3, which equals minus 24.75 kilonewtons. All right, that is a partial answer. Always put a box around a partial answer because it's good for extra credit points. Okay, so let's go back to the words of the problem statement and see what we are trying to do. So we are determining the resultant force and specifying where it acts on the beam measured from A. And so we found a resultant force, but to find where it acts on the beam relative to A, we have to start thinking about moments. And so A has been specified as our point of reference right there. And so I am going to begin by calculating the moment at A. All right, and I'm going to see if I can just kind of write this a little bit big. So the moment at A is going to equal resultant force F, resultant 1, which is minus 6.75. And then we have to think about where to put that, or what distance to kind of put in here to find the moment from this 6.75 kilonewton force. So stated differently, what I am saying is that area 1 has a resultant value of minus 6.75, and it is located somewhere on this beam, and I'm putting down where it's going to wind up going. And so if you remember from class that we have that for a triangle, the resultant force is located 1/3 of the way along from what I call the heavy end of the triangle. And so right here at 1/3 of 4.5 is where we will locate that force. In other words, at 1.5. So to expand that, 1.5 equals 1/3 of 4.5, and I am locating it at the heavy end of the triangle right there. All right, so we write 1.5 in there. So we have a force, and we have a distance, and so that's a moment, and so we're in good shape. So the force is downward, but what we need to think about is what would be the relative rotation of this force, force that I'm indicating right there. What would be its rotation relative to A? And the answer is that if things were allowed to move, this force would cause a clockwise motion around A, which means that it is negative. And so I've already got a negative sign in there, and I'm going to leave it there because it is indeed negative. Next, we want to add in the moment from F2. And so the resultant force from FR2 is minus 13.5, so we will have a 13.5, and it's going to also cause a negative rotation. So we have negative 13.5, which is FR2, and so what distance does force 2, where do we locate this force 2? So I'm going to put force 2 in a red color. And so I am saying that force 2, this negative 13.5 kilonewtons, we need to situate it somewhere in the middle of, well, we need to situate it exactly in the middle of this rectangle. So FR2, we can envision as being right there. So what is half of 4.5? Well, that's 2.25. So that's 4.5 over 2. All right, and now we have a third element. The last element that we need to think about is the yellow box, the area 3. And so we will have a third element. That third element will be minus 4.5 kilonewtons. and we're going to multiply by its distance. And so this force, we want to locate it exactly halfway in the middle of this rectangle. So that means it's going to be at a distance of 0.75 from B, which means that its total distance will be 4.5 plus 0.75. What is 4.5 plus 0.75? Well, that is 12. That's a 5.25. All right, we're almost done. All of these forces are going to cause a negative rotation, and so those negative rotations are shown by the signs here. They are all negative, and when we add all these things up, we find a total value of moment of minus 64.25 kilonewton meters. All right, so these three forces create that moment about A. And what we want to do is find out where to put this resultant force Fr, this single resultant force on this beam, so that it will create the same moment or the equivalent moment. In other words, this value of minus 64.25 has to equal some distance, right, times negative 24.75. And so now we solve for distance. X will equal 64.25 over 24.75, which is equal to 2.59 meters, which is our distance. And so to summarize, and I'm gonna kind of see if I can find a way to clearly show this. What I'm saying is that this force right here, this 24.75, if we just locate it at exactly 2.59 along the way from this beam, and so I think that's going to be at about, let's see, that's 4.5, 2.5, it's going to be about in this neighborhood, right about there. So if we locate this force right here at that location of 2.75 from A, that will be the equivalent force. So the answer is located there. Our resultant force is negative 224. We'll round it up to 24.8 kilonewtons. And that's it.